So in the first unit, we talked about how fluids can exert pressure on an object, and that relates to the force at which the molecules of the fluid are striking the surface. So when an object comes in contact with a fluid, it is experiencing a force. So now we're going to go back and we're going to kind of look at Newton's laws and the sum of all forces, and introduce a new force called the buoyant force. So if we have a scenario like this, where you have an object and it's submerged in water and it's actually suspended in the fluid, so it's not sinking down towards the bottom and it's not floating up towards the top, but it's suspended in the center of the fluid. Well, if we were to draw a free body diagram for this, we know that because we're on the surface of the Earth, we have the force due to gravity, which is the weight of the object pulling it down towards the center of the Earth. However, it's not falling down, so there must be some equal and opposite force that's causing it to remain in this static equilibrium. So that force must be upwards, right? And that force is actually called the buoyant force, and I usually write it with an F sub B. Now, the buoyant force, so essentially if we think about it in that way, is an upward force that is exerted by a liquid on a partially or completely submerged object. To give you some other sort of frame of reference, so if we think about floating in a pool, if you're in fresh water, there is an upward force that pushes up on you. But if you're in salt water, so if you're in the ocean, it's a lot easier to float because there's more of an upward force. So we know that the buoyant force has something to do with the density of the liquid. The more dense the liquid, the lighter you feel. Even if we compare it to the fact that, on Earth, we're essentially in a fluid that is the gas of the atmosphere, and you feel a lot heavier than if you're floating in water, which has a greater density. So it has something to do with the idea of apparent weight, what you seemingly weigh, what you feel like you experience, or what a scale would actually read when something is submerged. And we can use that to figure out what the buoyant force is on an object. So the apparent weight, if we wanted to figure out the upward buoyant force, we would take the gravitational force, so your real actual weight, and then if you were submerged in the fluid, we could figure out what your apparent weight is by seeing like sort of what you weigh while you're in the liquid, and the difference would have to be the upward pushing buoyant force, right? So if we look back at this free body diagram, you have your weight pulling down, and then the buoyant force is pushing up. So if we were to use a scale to measure what this is, the difference between these two would be your apparent weight. All right, now Archimedes is given credit for actually figuring out about buoyancy and defining buoyancy. So when you place an object into a liquid, it's going to displace a certain volume of that liquid that's equivalent to the volume of the object. So in chemistry, you learn how to measure the volume of oddly shaped objects by putting them into a liquid and looking at the difference in the volume. So here I have a graduated cylinder. It's at about 23 milliliters. And when I put this object in here, the water level rises to 30 milliliters. So I know that the volume of this object is 7 milliliters. However, it's important to note that the buoyant force that an object experiences really doesn't have anything to do with the object. It has to do with the fluid that it's in, or the density of the fluid that it's in. So buoyant force is truly defined as being equal to the weight of the displaced fluid. So if we were to calculate it here in a different way, we would have to take the mass of the fluid displaced and multiply it by gravity. And knowing that we have the density of a lot of common fluids, we can also relate, instead of having mass in the equation, we could have rho times v, which is essentially using the density equation to sub in for mass. So you would have the density times the volume of the fluid that is displaced times gravity. So in this instance here, 7 milliliters of this fluid has been displaced, and so if we say that it's water, we know that the density of water is 1 gram per milliliter, or 1,000 kilograms per meter cubed. So we could figure out and quantify the buoyant force on this object as a result of the fluid displaced. That also brings up an interesting point. So if I have two objects here, and say this object that I place in here is made out of lead, which is a really high density, or if I put something else in there that has a relatively low density, if they have exactly the same volume, then they are going to have the same buoyant force, or experience the same buoyant force, because the volume of the fluid displaced would result in the same buoyant force. So the density of the object, the mass of the object, really doesn't matter. It has to do with the fluid that is displaced by the object. And there'll be some questions like that on your classwork assignment. All right, so if we were to look at some different examples of objects that are either partially or fully submerged, and we'll look at some with different forces as well. So here we have another example of an object, but this time it's actually floating on the surface of the fluid. So instead of being completely submerged like the first instance, only part of it is underneath the surface of the water. So if I were to look at this, I could draw a free body diagram. It would look very similar. I would have the force gravity down and the buoyant force up, and they would have to be equivalent to one another. But remember that the buoyant force would be equivalent to the volume of the displaced fluid, so only the volume of the cube that is submerged underneath the surface of the water. Whereas here, when we have that fully submerged object, then we would have the weight of the object being equivalent to the buoyancy again. However, in this case, if we looked here, the volume here would be equivalent to the total volume of the submerged object, as this was only the partial volume that was below the surface. Now we can also incorporate in some other forces. So in this case we have an object that is suspended by a string in a fluid. So instead of just having two forces, we have three forces, but we still have this idea of equilibrium because it's not moving. So we would have the gravitational force down, and we would have the tension up and the buoyant force up. So if we were to write a sum of all forces equation, I could have tension plus force buoyant is equal to force gravitational. So this would be, this is going to be similar to something that you'll do in the lab as well as what you'll see on the classwork. And then of course we also have springs that we've looked at before. So spring force, remember we use Hooke's law, so spring force is kx. And so here we would have two upward forces, spring force and buoyant force, equivalent to force gravitational, and we could use that to figure out buoyant force. So just keep in mind that we will be combining this with previous sum of all forces problems, and we will be looking at ways of calculating buoyancy like this. So the last thing that I want to show you is this, and this is going to be used in one of your labs. So this is the idea of using apparent weight and actual weight and buoyancy in order to figure out unknown densities of submerged objects, or the density of the fluid of which the object is submerged. So if we derive out this equation, we end up seeing that the ratio of the density of the object to the density of the fluid is equivalent to the actual weight of the object over the buoyancy that the object is experiencing. So here we have the weight of the object over the buoyancy, or the buoyant force the object's experiencing. And remember that we can use apparent weight to figure this out. is equivalent to the density of the object over the density of the fluid. Here is a sample problem. I'm not going to go through that here in the video. You'll actually be doing this and experimenting with the lab, so I'd like you to try and see if you can figure it out first, and then we can come back and do these examples if you need help figuring it out. So that is buoyant forces.